Good day. My name is Jim Durstein, and the case history today will be looking at well log, database validation, and normalization using multi-regression analysis. The original objective here was not log database validation and normalization. We wanted to estimate the impedance of the 3D seismic data using model-based inversion technique. So to do that, we're going to require the 3D seismic data, the borehole, geophysical logs from the boreholes, and interpreted seismic horizons. So typically what we would do is we would create synthetic seismograms, correlate them with the seismic, and extract wavelet, its amplitude and phase spectrum. Then we'd create a low frequency model from an initial impedance model, and we'd perturb that model based on the amplitudes of each trace in the seismic volume. So what happened? Well, here we're looking at a horizon slice taken through the roof of the coal, and what we can see is the area that the ground engineers are particularly interested in, because we're looking for instability in the roof. In this particular case, the blue means higher impedance. The yellows and greens mean lower impedance. And here you can see a channel feature coming through, and perhaps another one coming through there. These borehole locations are shown in black. And we have this area in here which is very low impedance, suggesting that there may be a problem in there. But it looks a little odd. It looks a little centered around the borehole location. So what we'd like to do is we'd like to determine whether these low values are real. How significant are they? And we want to make sure it's not a problem with the logs, and how could we go about validating this? So what we're going to do is we're going to use a multi-attribute transform, and we're going to predict log properties from other well logs. We're not going to use seismic in this particular case. We're going to do our analysis in depth. So we require a choice of logs, a target log, which in this case is density, and we're going to use a set of external attributes, which is the other well logs from the same borehole location. The multi-attribute transform is derived, which may be nonlinear or linear, using a subset of the attributes and the target logs. The attribute subset is determined by a process of forward stepwise regression analysis, which derives and ranks increasingly larger subsets of the attributes. Cross-validation is used to estimate the optimal number and reliability of the attributes, and also it involves the systematic removal of each well from the training set, and then the transform is rederived with the remaining wells. So now we're going to show 4 separate borehole locations: R1287, R1328, R1342, and D838. The D838 was recorded at a different time, or obtained at a different time, a different vintage than the other ones. The original logs are shown in black. The model density logs, based on the multi-attribute transform, are shown in red. So the density log predicted from some combination, in this case, of sonic and gamma logs. Notice that for each well, the predicted log was estimated without the original log at that location. The transform function was derived only using the other wells. So we can see quite clearly that there's a discrepancy between the predicted log in red and the original log in black at the D838 location. So this may explain why we've got such a model-based impedance is showing such a low impedance at around the D838. The model's wrong. So this particular log needs to be normalized or matched to the other logs, and here's a way of doing it. We can use the multi-attribute transform. So let's look at this in terms of a cross plot. So the cross plot on the upper left-hand side is showing all these boreholes including the D838 location, and we can see a cross correlation of about 0.95 and an error of 133 grams per centimeter cubed. This isn't a bad match. But what we can see is the data points from D838 are plotting up here, offset from the main group of the data. Now, if we take that information, that density information out from the cross plot, we can see we get a much better fit, 0.98, and our error has been reduced significantly. The logs creating a transform based on the logs, including the D838 location. We can see that there's a lower correlation coefficient and again a lower error. And we can see it will only improve if we can get rid of the bad data point. Bad teacher, bad student. So now we're going to look at revisit the horizon slice that included the D838 location in the original inversion and see what happens when it's removed. Well, you can see quite clearly the importance of having good borehole information to build a model, because we are building a model based on sparse data. It doesn't matter how many borehole data points we use to create the model, we're still trying to predict it in places where there is no low frequency information. And having a bad data point in there doesn't make the job any easier. So here we can see from a ground engineering point of view, this area doesn't look problematic with respect to roof stability compared to what it did on the original inversion. So a revised procedure, if we're going to do model-based inversion, it's a pretty good idea to validate and normalize your well log database before you use these borehole locations and their logs to create a low frequency model. So then we'd create the synthetic seismograms, tie the wells, extract the wavelets, build a low frequency model and estimate the impedance accordingly. Or an alternative is we can do an inversion to estimate a relative impedance where we don't use the horizon information. We don't use the borehole information for the inversion. We estimate the reflectivity, calculate the relative impedance, then all the borehole information we can use to validate the accuracy and the limitation of the relative estimation of the relative impedance. So in conclusion, if we're going to do a model-based inversion, we need an accurate model. So if we're building that model based on well logs, then we better make sure that they're consistent within each other. If one borehole has been collected maybe 5-10 years prior or to the other one, then there's a good chance there may be issues with that require normalization. Also, borehole conditions, areas where the caliper log goes a little out of whack, there it's probably going to affect the density log first, and this will have an impact too on the logs. And if it's not caught, it will be embedded into the model-based inversion. I want to acknowledge MIM for permission to show this log data from the Newlands mine in the Northern Bowen Basin, and I'd also like to acknowledge the use of Hampson-Russell's multi-attribute modeling technique developed by Hampson-Russell, which is now part of CGG. And for a reference on this technique, Dan Hampson's paper from Exploration Geophysics in 2000 is a good reference. Thank you very much. I enjoyed this presentation and hope to do more. Thank you.